We are Team 3 and this is our interim presentation on the assembly analysis of a master lock 6-pin cylinder padlock. Team 3 is comprised of Michael, Nicholas, Daniel, Leah, and Holden. A padlock in general is a portable lock meant to bar something from access or entry. The top shackle of a padlock is to be looped between two halves of what is meant to be locked and pressed into the body. Once in the body, the shackle can only be released once the corresponding key is inserted. This key will depress 6 pins to specified heights, allowing the cylinder to rotate and release the shackle. The shackle of the master lock padlock is made of hardened steel to prevent break-ins, while the body is made of weatherproof brass.
Here is our exploded view of our lock assembly. It features 8 unique components, and they are not designed for disassembly or repair. For simplification, certain parts have been grouped into subassemblies.
Here we have the bill of materials showing a breakdown of the quantity, material, and manufacturing processes for each part of the padlock. The 5 key pins, each having a unique length along with the different pins, springs, and plugs involved in the assembly of the latch and shackle, have been grouped into the subassemblies highlighted in gray. A majority of the components for the padlock are made from brass, except for the steel springs and the shackle, made from cut-resistant hardened steel. As well, most parts are manufactured through a combination of machining processes, with the pins and cylinder requiring methods beyond the capabilities of standard machining operations, like Swiss turning and broaching.
Here's our liaison diagram showing the components from the exploded view and their connections. Of note, we have 5 key pins arranged in a column here, as well as 5 driver pins. Each key pin connects to one driver pin, and each key pin connects to the cylinder and the key, whereas each driver pin connects to the cylinder and the housing.
In order to give context to the key characteristic focus area, let's first take a look at the full cross-section of the product. Narrowing in, we see KC1, which describes the distance between the driver pin chamfer and the cylinder shear line. In order for the correct key to open the lock, the cylinder shear line must lie below the driver pin chamfer. As indicated on the figure, KC1 should be a positive value and is delivered through the cylinder, key pin, and driver pin. KC2 describes the function of rejecting an incorrect key by evaluating the distance between the housing shear line and the key pin chamfer. If the incorrect root is higher than the reference root, the key pin chamfer must lie above the housing shear line in order to reject the incorrect key. In our depiction of KC2, an incorrect pink key is shown behind the reference root of the correct key, showing the mismatch. KC2 must be positive and is delivered through the housing, cylinder, key, and key pin.
Here are our KC delivery chains. And so we could see KC1 is the distance between the cylinder and the driver pin. So the liaisons on the delivery chain for this KC include cylinder to key pin, key to key pin, cylinder to driver pin, and key pin to driver pin. For KC2, it's the distance between the housing and the key pin. So the liaisons on the chain include housing to cylinder, cylinder to key pin, and key to key pin.
These KCs and their reciprocal cases can be in conflict for a designer that wishes to save cost on part tolerances. The extra design margin on chamfer is necessary to allow the correct key to open the lock, despite variations in part tolerances, can also allow a wider set of incorrect keys to open the lock.
Thank you for listening.